Chapter is work, energy, and power. So we will be talking about work done by a constant force. Work done is nothing but force acting upon an object to cause a displacement. So let us consider three diagrams. Part A, force is in same direction and the displacement is in same direction. That means there is no angle between F and D. That means my theta here is 0 degree. So what I can get from this is, as you know that cos 0 degree is 1. So that means my work done is F dot T. Let us consider the second one. Suppose I have a force in the direction 30 degree and we can see the angle between D and F is 30 degree. That means my work done will be F cos 30 degree dot T. Let us consider the third one. My force is in y direction and my displacement is in x direction. That means you can see that if the angle between F and D is 90 degree. So work done will nothing be cos 90 degree is actually 0. So my work done in the third one will be 0. So work done is nothing but depends on force and displacement under the influence of force. So you must remember that F vector is defined as F cos theta and D is the same. So therefore we get this solution for work done. The next part is work done by a variable force. Variable force Variable force means that we have different forces applied at different displacement, as you can see in this graph. So if we need to study this graph, we have to consider work done as area under the graph. So my W will be area under the graph. So if you need to find area under the curve, you have to take integration into play. So you can see the initially the displacement is 0. So initial one will be 0 and it will be S here because the final one, that is S. Now we have F and my variable will be ls, that is displacement. So this is my work done under a variable force. Now the second thing is energy. So energy is actually a physical quantity which enables a system to do work. Now we have one energy, that is mechanical energy, and that energy is divided into two parts, that is kinetic energy and potential energy. So kinetic energy is the energy possessed by the body by virtue of its motion. So whenever we talk about according to motion, then we talk about kinetic energy. When we talk about potential energy, it's about how height. So the formula for kinetic energy is half mv square, and mass and velocity are always positive, so kinetic energy is always positive, and it does not depend on the direction of motion of body. So remember that it doesn't depend on the motion of the body, it depends on the velocity and the mass, as you can see. So one relation is there between kinetic energy and momentum. So it is kinetic energy E square 2n. The graph is given here for you to understand how kinetic energy is dependent on momentum. So you can see that kinetic energy is actually proportional to p square, momentum square. So you can see that there is an increase in the graph as we move on towards potential, towards momentum. So there is an increase and the kinetic energy increases as we increase the momentum of the body. Now we have another relation between kinetic energy and potential. So this is nothing but a replace of above above formula. So it will be k 2n p square, and p square, if I take it there, it will be under root k 2n under root 2n equal p. So as you can see that p is proportional to k square, k under root k. So the diagram will be a straight line. As you can see that we have relation between p and k. So p and k as a variable. So as you increase p, there will be increase in under root k, kinetic energy. Now the next thing is potential energy. So potential energy is actually energy possessed by the body by virtue of its position relative to other. So basically in this case we talk about height, and potential energy is defined as mgh. So must remember that kinetic energy is dependent on motion and potential energy is dependent on height. So let's start with the next topic, very important topic, work energy theorem by constant force. So it states that the change in the kinetic energy of a particle is equal to the work done on it by the net force. So suppose it is Kf minus Ki. So the final position. So work energy theorem says that we have it says that change in kinetic energy of particle is equal to work done. So let us say that kinetic energy is something here, Ki. So suppose we have Ki here and we have Kf here. So what will be the work done here? So you just need to take Kf minus Ki, and you know that we have half mv square, so I will remove mass will be same, there won't be any change in mass if we change the kinetic energy from initial position to final position. So we will be writing 3f square minus half mvi square. So this is the work energy theorem by constant force. The next one, we have work energy theorem by a variable force. In the last one, it is a constant force, and in this one, we have a variable force. So whenever we have a variable force, we take integration into account. This is xi, xf, and ki, kf. So this is the work done because this involves ftx and this involves kinetic energy. So that's why they are equal, because work done is nothing but change in kinetic energy at initial position and final position. So that's why the formula is here. It is same, but in this case we have a variable force. That's why we need to take integration into account. Now the next topic is power. So power is actually defined as the work done over a period of time, or you can say it is rate of work done. So whenever we talk about rate of work done, or whenever we talk about rate, it is always with respect to time. So you can see that we have del W over del T. Now you know that del W can be written as F dot dr. So I will replace this with F dot dr, as you can see in the second one. In the third one, why it is written as V here? So del R over del D is nothing but velocity complement, F dot. So either you can define it like this or like this. Now we have the most important topic, that is potential energy of a spring. So Let us take a block here. So you can see one block is there at a relaxed position in the first figure. Initially, I would be taking the spring its natural relaxed condition. If we compress the spring in the second condition, if we compress the spring by a constant force F, then the work done by the force is stored in the spring as the potential energy. Now, when you compress this box, the potential energy will be stored in this particular box. Now, when the work done by the force is stored in the spring as a potential energy, now when we extend the force, it will lose all the potential energy and will be extended more towards the left side. So this is what the potential energy of a spring. Now the last topic says the conservation of law of mechanical energy. Mechanical energy, as you know from the last slide, involves kinetic energy and potential energy. So when we talk about kinetic energy and potential energy, they are actually conserved whenever we take into account mechanical energy, as it doesn't depend on time. So their constant remains their motion remains constant. So therefore, if we take kinetic energy and potential energy, their states remain the same. It states that for conservative forces, the sum of kinetic energy and potential energy at any point remain constant throughout the motion. So that we can write because they don't depend on time. So it is K1 plus U1, K2 plus U2 equal K3 plus U3. So that's the end of this lecture. We'll cover MCQ questions for NEET in the next one.